Hello, everyone. We'll get started. The agenda for today is to discuss some aspects of power factor correction, especially the control side. We'll start with a very brief introduction on power factor correction, something that we've already covered in another webinar, but yeah, just for some reminders. Then we'll discuss more specifically the boost PFC control and some improvements that can be added to the basic control. And in the second part of this webinar, we'll also cover the Bridgeless PFC and some of its advantages. And as Julian said at the end, you'll have some time for questions and answer. We'll try to keep 10 to 15 minutes to answer your questions. So let's start with power factor correction, some brief introduction. So first of all, power factor correction is also known as PFC, and that throughout this webinar, I'll probably use more PFC than power factor correction, just for the to avoid the repetition and to make it shorter. So power factor correction, the goal is to correct power factor. And what is power factor? It's the ratio of the real power over the apparent power, or what we also call active power. And if we take the example of a pure resistive load, it has a power factor of 1, which means this translates into really the fact that the input current is in phase with the input voltage and with a sinusoidal shape. So if you know, we assume, of course, in all this that the input voltage is the grid voltage, so a sinusoidal input grid voltage, and the current, if the current follows the voltage in shape and in phase, then the power factor is 1. Now, for a typical power supply, most of them, they will have some active electronics, and in front of it, a bridge rectifier and a filter. This is to convert the AC input into a DC voltage that's usable by the load. In that case, the current only flows during the conduction of the diodes, and depending on the size of the filtering capacitor and the amount of current that's drawn by the actual active load, then this conduction time might be very short. And as a result, you see the input current shape here. It's very far from a sinusoidal waveform. It's usually just peaks of current during the recharge of the capacitor, and in short duration, and also possibly out of phase with the input voltage. And in that case, also, it tends to create a large RMS current, because this peak here is quite high compared to the average. So you get large RMS current circulating. So you have high reactive power, which is, apparent. So the sum of active plus reactive is the apparent power. So the more reactive power you have, and the lower the power factor. So if we take this generic power supply with its input rectifier stage, then again, you have the sinusoidal input voltage, but just a short conduction for the input current. And we add PFC to it. So let's say we add this PFC stage in between the bridge and the filtering capacitor. Then what this stage does is to force the input current to be sinusoidal. So that's really the goal and the real concept of power factor correction. Now, PFC, there are many ways to achieve or to increase, let's say, the power factor. So it could be passive. In its simplest form, let's say you just insert a large inductor in between the diodes and the capacitor, and this forces the current, if the inductor is properly sized with respect to the size of the capacitor, to force a sinusoidal current at the frequency of the grid. So this is one way. although that inductor can be big, of course. There's also such thing as a valley fill, which I will not discuss today. And it can also be active. And active means that it's a switch mode power supply, basically. So it could be a buck, a boost, a flyback, and etc. But really, when we look at all the trade-offs, so if we're looking at the power factor that it can achieve and the amount of distortion, as well as the efficiency, the total size it takes on the board, and of course, it's related to the size, but its cost. Then the most widely used today is the boost PFC, because it brings the most advantage at the lowest cost, and this is what we're going to cover in this first part of the webinar, because it is the widely used topology. So let's go and look in more details at this boost PFC and the methods for control. So first of all, again, a brief reminder of what a boost is. If you see in this implementation, so still this diode bridge rectifier connected to the grid input. There might also be a filter here that we are not representing, but it should probably be there, most likely be there. And then we have this boost stage. So the boost is an inductor with a switch to ground and then a freewheeling diode. And this will create here an output voltage, which is higher than the peak of the input voltage, because a boost is a step-up solution. It's a rather simple implementation, as you can see, because we only have one switch, one diode, plus this inductor, and of course the control and some feedback here to sense the output voltage and regulate it. But it is rather simple implementation. And as a result, it can have quite a high efficiency, which is also a good thing, because we're adding a stage in addition to a power supply. So we want this to be minimally invasive in terms of efficiency. Also, what's interesting is that it can operate at low input voltage, because this grid voltage here will, because it's sinusoidal, will cross zero every cycle. So it will be alternating between low and high voltages. And if we want to control the current as much as possible to follow the voltage, then the controller and the stage here has to be able to operate at low input voltage. So this is the boost PFC. I'll talk about the control method, but first, let me discuss briefly about some of the reasons why the PFC is added. So in reality, it doesn't really improve the behavior and the performance, let's say, of the switch mode power supply, the conversion from AC to DC. But it is mandatory in many situations. And there are standards that are driven by different organisms around the world, in different regions of the world, different countries, depending on the market, the end market, the type of application, the type of end product that is used. And so these standards ask for higher or lower minimum power factor for an AC to DC power supply, or anything that's connected to the grid. And so sometimes there are still applications where it's actually not necessary, or there are some loopholes, let's say, where it's not necessary. More and more, it's mandatory to have some form of power factor above a certain level of output power. This is to ensure the quality of the grid voltage and also not overproduce electricity. So this is driven at international level by committees. So as a result of this, and because this varies a lot from region, from country to countries, from end products to end market, etc., then a lot of different type of PFC circuits and also PFC control are suited for different situations. Some may work for some applications because the requirement is lower, but for others, it may not be sufficient, so you have to use a different method. And in addition, of course, the standards, they tend to evolve over time or to be added to new markets which didn't have them before, or just, the levels can become more stringent, etc. And so as a result, again, these circuits, which is suitable for one case, may not be suitable for another case. And more importantly, it can become, it used to be acceptable, but become obsolete for some applications. So an example of this, for example, it's again with the Boost PFC. One of the simple control methods that we can use is just run it at a constant current. So the control will ensure that the input current keeps constant over the cycle of the input voltage, sinusoidal input voltage from the grid. So by doing this, we increase the conduction time of the diode of the bridge. You can see it's conducting the whole time. But of course, this is not sinusoidal. The current is square. It's not sinusoid. So you can, of course, argue that a square wave, as you can see, you can rearrange it as a superposition of many sinusoidal waveforms added together. This is a Fourier series transform here. You can say it's a very highly distorted sinusoid, but it's not sinusoidal. So the PF will be better than without anything, because we've improved that conduction time, and we have a current that's in phase with the voltage. But because it's not sinusoidal, that it will not be very high. So you can probably reach a power factor of 0.7, but the distortion is high. So for certain cases, it used to be sufficient, or may still be sufficient in some cases, but most like in most other cases where a PFC is needed, then it will not be sufficient. So for this webinar, we will only look at the most practical methods and what's widely used again. So we'll concentrate on the Boost PFC and on control methods that are sufficient, let's say, to bring the power factor to a high level, enough to cover most of the standards. So let's start with the first method I want to cover today. It's the constant on-time boundary conduction mode. So boundary conduction mode, BCM, which is also known as CRM for critical conduction mode. This means that the current that the system is operating right at the limit between discontinuous and continuous conduction mode. So the current will keep flowing into the main inductor, and as soon as it reaches zero, we'll turn on again the main switch so that to keep the current flowing, but right at the boundary. So this method is, let's see in details what it does. So we're relying on the fact that when you apply a voltage across an inductor, there will be a current flowing into it, and that current is proportional to the input voltage. If you know the basic equations for an inductor, you know that V equals L di over dt. So if you rearrange this, you can see that the input voltage, so we're looking here at the average input voltage, so the one that's represented in blue. So the average is half of the peak current, so the DI current in the inductor during this on time here. It's the average is half of this, so we can say that it's the input voltage divided by the inductor times the on time and divided by 2 to get the average. So if we want the input current to be in phase of the input voltage and in same shape, sinusoidal, then we want this ratio of the input voltage over the current to be a constant. So this ratio, we can call it R equivalent, so an equivalent resistor. It's equals to 2 times L over T on. So you see that 2 and L are constant, of course. So if you want this to be constant, and as a result have a perfectly matched input current to the input voltage, then you need this on time to be constant. So as long as you drive this boost with a constant on time and restart it as soon as, start the next T on, the next cycle, every time the current reaches 0, then you will ensure a perfect power factor. And this is done very easily because there's no need to measure, for example, the input voltage and do complex treatment of it to get the input current. Instead, just by ensuring a constant on time and the critical conduction mode, then you will, as a result, automatically get a sinusoidal input voltage in phase with the voltage. So this is a very simple architecture. Simple means usually low cost, so this is a good thing. Also, it ensures zero current switching because we wait for the current to reach 0 before turning on the FET again. So this has some advantages of low noise, especially with because we can have valley switching of the MOSFET, so as low voltage across it as possible when we turn it on. And yeah, so low noise is also a good thing. And it is also good for efficiency when we can run it at zero current because there are less losses for example, in the diode. Now, of course, this is not perfect. There will always be some disadvantages. The main and obvious one is that to get this level of current, you need to have twice as high a peak current. So this means that we have quite high RMS current flowing and quite high I peak, which practically limits it to a certain power level, which is usually around 300 watts. Above that, yeah, it starts to be a lot of losses created by this current. Also, the DI DT, the higher the peak current here, and the higher the DI over DT, and this also creates some issues also in EMI, for example. Of course, you can always add more phases. So interleave 2 of boost stage like this, both running in CRM, to go to higher power. In that case, you can probably reach, I don't know, at least 600 watts, let's say double of that. So for higher power, another method consists in running in CCM, continuous conduction mode. In that case, you see the average current in blue, which is trying to be a sinusoid following the input voltage. And the actual inductor current this time doesn't go down to 0. Instead, there is some delta I around that average input current, there's delta I that we can control. And as a result, you see that the peak current is not much higher than the average current. So the ratio of peak current over average current is much less, which means that we have much lower RMS current than for a given average input current than in the case of the BCM control. Practically, how we do that is somehow we need to have a current reference which is following the input voltage waveform, input voltage sinusoid. And we add on top of that a certain amount of peak current of delta I. And this can be a constant on-time control, or this can be a fixed frequency control. There's different ways to achieve that. But the main thing is you need to have this to create this shape, this reference shape for the current, so that it can follow the input voltage. So in that case, it's not it cannot be done automatically. It needs to add some sensing of the input voltage and some treatment algorithm on the involving the input voltage to get the input current reference. The good thing is because we have this much lower RMS current and this much closer peak current to the average, then we can use this method for the boost PFC for higher power, and practically we can go quite high, and up to a kilowatt is normally feasible. And of course, again, interleaving is always an option, so you can always interleave 2 CCM stages to go even higher in power. As I said, because we need now to create that reference for the current, and then there's more complex treatment, and the architecture itself of the IC tends to be more complex. For example, here I give an example from the HR12XX family from MPS. In this case, it's a digital PFC, but it doesn't matter. There is some mathematical treatment extracting from the input voltage to create the reference for the current. And this complex mathematical treatment has a cost in die size and in complexity of the IC itself. So this translates into a higher cost of solution. Also, because now we don't wait for the current to become zero, there's a more hard switching, which has some consequences and maybe some losses associated to it, and also higher noise generated. So EMI needs to be filtered, controlled. But the main advantage is it can deliver higher power. Yeah, something I didn't mention, but of course and it's valid for both the BCM and the CCM control. The power itself can be controlled by altering the level depending on the feedback that we get from the output. So what's important is that it stays constant. So the control loop via the feedback needs to be at a very low frequency so that it seems to stay constant with regards to the input voltage shape. All right, so these are the basics really of PFC control and the most widely used control methods. And now we'll discuss some drawbacks, or let's say some imperfections that are linked to the reality and the implementation of these methods, and how to improve the PFC or the PF, sorry, in these conditions. So we'll look at efficiency improvement, power factor improvement, also distortion. So first of all, efficiency improvement. So again, I'm going back to the standards because now more and more the standards not only ask for a given or a minimum level of power factor at full power, but also at different load scenarios, including quite light load conditions. And in most cases, this basic control methods, they're not doing very well at light load. So, for example, if we take the BCM or CRM mode, so the first case that we discussed, to lower the power, of course, we will lower the peak current in the system. So the average is getting smaller and smaller, but still sinusoidal. The problem is if you go back to maybe to that slide, that would be easier if I show you. Here, if you decrease the peak current, the frequency will tend to go up because this boundary conduction here, the time where the current goes back to zero and we turn back on, will get closer and closer to the previous on time. So the frequency tends to go up, And as a result, when the frequency goes up, switching losses goes up as well, and efficiency goes down. And because the standards, in addition to asking for high power factor, including at light load, also ask for good efficiency in all conditions. So one way to overcome this and to prevent the switching frequency from going too high and the efficiency from degrading is to, at some point, allow discontinuous conduction mode. But if, again, we look at some equations here of this constant on time boost control. So now if we're adding some dead time before the next conduction time, so this allows to increase the off time, and so to ensure that we are in discontinuous conduction mode. So instead of restarting here the MOSFET right away, we wait for some time to be fully discontinuous. So if we now look at the expression of the current versus the input voltage, there's a new contribution here from this dead time. So we can call it sort of a duty cycle of the dead time. And if we again look at this equivalent resistor, we now see that it's 2 times L over T on that we had before, but times this duty cycle. So if we want to keep the PF high, it's not T on that needs to be constant, it's T on times the duty cycle. Practically, this means that when you insert a dead time here, you need to adjust the on time proportionally so that you keep that ratio or that factor of T on times the duty cycle of this dead time to be constant. If you ensure that, then you can still ensure a good PF in discontinuous conduction mode while the load decreases. And if we look at the switching frequency, so you see that the switching frequency increases as long as we are CRM and we decrease the power. And at some point, we go into DCM, and then the switching frequency decreases, which means that the efficiency will stay high. It will, at some point, it will decrease as well, but this will keep it much higher for a longer time when the power decreases. So this is one improvement for the borderline conduction mode case. Now, this can also be applied to CCM. In CCM, of course, if the power decreases, at some point it becomes beneficial to go DCM as well. And it can actually be running in what we call multi-mode. So CCM at high line, high load, and then maybe going through a borderline conduction mode for some time, also in certain conditions. And then when the load decreases and the input voltage is low, then it can run into discontinuous conduction mode. We even have some parts that have different types of discontinuous conduction mode, depending on the level of loading, to ensure that the efficiency is as high as possible. So it's running, let's say, constant frequency CCM, then constant frequency DCM for some time, and then at some point, we'll even allow it to go into variable frequency DCM. But the key here is to control always that dead time that is inserted, and to keep maintaining a constant factor so that the input current is still in shape and in phase with input voltage. So it means there's a more complex algorithm because that dead time is not, we're just not letting it be added automatically, but we control while we add the dead time that the on time also follows to keep the power factor high. And as a result, you will see something like this depending on the loading and the input voltage. But you can see that here in the middle, the controller is running in CCM. But then when it decreases and at some point it reaches 0 here, then it will run in BCM for maybe a certain amount of time. And then for the rest of the sinusoidal waveform of the input voltage, it will run into DCM. And then if you increase or decrease the load, then this shape will move up and down, and there will be more or less time in discontinuous conduction mode or in continuous conduction mode. So this is a way to keep a high PF at light load while ensuring a high efficiency. Other improvement to the basic, let's say, control methods comes from this input cap that I'm showing here. So the drawback. So first of all, this input cap is needed because the current in the inductor here, as we saw, is as a high frequency component, right? It's a switched current. The inductor alternatively the current is alternatively increasing and decreasing in the inductor, controlled by the switch. But what we want on the input is an average sinusoidal current. So this capacitor here is here to filter this high frequency component of the current and to keep only the average current. So the one problem that this cap here brings is that at light load, there's not so much current flowing into the output and into the system, and this eventually not enough current to fully discharge that capacitor when the input voltage gets close to zero. So the voltage at this point after that will never reach zero, even though the actual grid voltage goes through zero, but this voltage here, which is the input of the PFC, will not reach zero. There may be also some other limitation of a constant on-time controller. For example, it may hit a max frequency clamp around the zero crossing, and all of these can create some high distortion, because if you look at the shape of the current, then this might translate in something like this, where the current actually is the conduction is shorter than the actual sinusoidal waveform. And there's a gap here, and this tends to have a high distortion. So what we want is try to close the gap and have it as close as possible. One way of compensating for that is to use variable on time. So with variable on time, we increase the on time when we get close to zero to force more current to circulate and empty that capacitor. And then also we compensate for this higher current into this area of the waveform by slightly reducing it over the peak to keep it close to a sinusoid and get that have this gap as small as possible. So this is called variable on-time control, and this is one way of improving also the THD. Another drawback, let's say, which is caused by this input capacitor, but as well also by the input filter, EMI filter, that's most likely in front of the bridge rectifier, is that, yes, the PFC stage controls its input current, but then in front of this PFC stage, which has a perfectly sinusoidal current, we have these capacitors of the filter that in which some current is also flowing through the capacitor. So at the IL level, which is the input of the PFC stage, the current is sinusoidal, but at the IN level, which is really connected to the grid, then there is this perfectly sinusoidal current plus a capacitive current here that introduces a phase shift. So we can also compensate for this. For example, here I'm showing an example with a triangular wave. So knowing here that there will be some current flowing through the capacitor, which is represented in green here, completely out of phase with the input voltage. Then we add a ramp to approximate more or less the shape of this current. Of course, if it could be better if it was a sinusoidal shape, but even a ramp is already a good thing. And the resulting, so the current in the input, the IL current, is purposely out of phase, so that once adding the current in the capacitor, the IN current becomes in phase with the voltage. So yeah, this is some sort of a feed-forward compensation, let's say, to compensate for this. All right. So for the last session of this webinar, we'll discuss Bridgeless PFC. And okay, let's start with why we're even considering Bridgeless. So I discussed quite a bit about this input bridge rectifier in front of the PFC, in front of the power converter. And you can see that at any time, there are two diodes conducting in addition to the circuit behind. So two diodes always in series. The problem with this diode is that they have non-negligible conduction loss. And, we have made quite good improvements lately on the PFC itself, especially using GaN switches, better control optimization, enhancement that I showed you, etc. So the efficiency of this stage has improved greatly, but the rectifier bridge in itself, it doesn't really change. So more and more, it becomes a major contributor to the losses. And here I'm showing an example where it adds to several percent of losses, up to 5% in this case at the low line, 115 volt AC, for a 400 watt power. So, and if you look at the heat generated by this bridge rectifier, it's really becoming important to the point that it's even limiting the density of and the size of the adapter. It cannot be smaller because of these losses here. So it will be beneficial if we can improve this and even get rid of it. If we look at the conventional boost PFC, I've already mentioned that there's a freewheeling diode, so there's already a blocking diode. So why do we have to add another blocking diode in front, right? It's just too bad because we already have that. So one way is to use one boost PFC for each alternance of the input voltage. So for the positive alternance of the sinusoidal input voltage waveform, we have one boost with its inductor, its switch, and its diode. And then for the negative alternance, we have another boost with a diode. So here the current only flows through that diode, and then through the body diode of the other FET to come back. And then when the alternance is the opposite, then it's the other diode that's conducting, and then through the body diode of the other FET. So we have one PFC boost on each line, so we double it. But in reality, if you do the count at the end, there are only two diodes now in series instead of three with the regular implementation. So you can definitely improve the efficiency by reducing the losses of at least one diode. So this is the basic concept of a bridgeless PFC, and actually, if you will, the evolution of this is the totem pole PFC, because if you look at this compared to the two boosts that I showed before, we still have a boost PFC, so with the inductor and a switch and a freewheeling diode, except we make it synchronous, so it can be reversible depending on the alternance. And then we add, again, we use MOSFETs instead of diodes to select the polarity. So when the polarity is positive alternance of the sinusoid, then one of these MOSFETs will be conducting, the other one will be blocked, and vice versa. So we have a fast switching pair of MOSFETs for the boosting effect, and then a slow switching pair of MOSFETs just for the selection of the polarity, so really the rectification. So we can look briefly at these waveforms. For the positive alternance, the MOSFET here, called D, will be conducting all the time, and then the boost will alternate between high and low of the two MOSFETs here. And so they will operate as a synchronous boost with the D MOSFET always on during the positive polarity. And then for the negative polarity, it's the same thing. The two fast switching switches will operate as boost, and now it's the B switch that will be on all the time, and D switch will be off during the negative polarity. If we make a comparison between a totem pole PFC and a normal PFC, so single boost PFC that we've discussed before, if you look at the number of active ICs, so we have for the totem pole PFC we have two. So we're considering GaN here to have the highest efficiency possible. So 2 GaN FETs for the totem pole. This is for the fast switching, so for the boost in itself. And then we have 2 MOSFETs, silicon MOSFETs for the polarity selection. And for a normal PFC, we have 1 GaN FET and 1 fast recovery freewheeling diodes, plus, of course, the rectifier bridge. And if we look at the efficiency of this for a given point of operation, here we're considering low input voltage and 300 watt GaN. Again, GaN is important because then we can reach with GaN an efficiency which is quite high. We're talking about the minimum point at 90 volt AC above 97.5% of efficiency. And at high line, it will go above 99%. So this can be really, really efficient. And a normal PFC will be at least 1 to 2% down in efficiency. So this is measured on a real board using a new controller from MPS, the MP45000, which is a CRM totem pole PFC. So that's really optimized for power lower than, let's say, 400 watts or 300 watts. So you see as the results is by using a totem pole PFC, getting rid of the rectifier bridge, then we have that 1 to 2% efficiency improvement. Of course, the controller needs to be a bit complex also because it has to be able to select the right polarity and control the FETs accordingly. But yeah, this is an efficient way to a good way to get to a higher efficiency. This concludes this webinar for today. I pass the control to you again, Julian, for the questions.
Thanks a lot, Nicolas, for the great presentation. So I want to remind everyone that you can mouse over the bottom of your Zoom meeting interface, and you will see the Q&A button. You can type in any question that you might have. As we are waiting for more questions to come in, I want to remind you that we are recording this session, and we will send you a link to the webinar within the next days. With this link, you can watch today's webinar on demand, and we will also send you a link to the PDF of the presentation. Please also check our MPS webpage for our webinar schedule to have a look at future sessions. So let's get started with the first question. And it is, I think this one refers to the totem pole PFC results. Nicolas, if you go to this slide, the question is how the efficiency of this topology is influenced. Depends this only on passive components and MOSFETs, or is also the controller which could influence it?
Yeah, of course, the passive and active components will play a role. There are losses in all areas of the power supply of the controller. But yes, also the control methods. So something I didn't say during the presentation, but this totem pole PFC can be controlled also as a CRM or as a CCM, and all sorts of enhancement can be added. So yes, actually the control will play a role, but of course the selection of the components is also important.
Okay, thanks a lot. So I think those two questions, next one, were referring to the bridgeless PFC slides. The first one is, could this type of PFC work bidirectional?
So the totem pole PFC, yes, practically yes, it can be controlled bidirectional because there's only switches, and so you can always switch them in opposite directions. So this is a possibility, and there's also one advantage of it versus other topologies. So in modern application, this can become interesting to be able to feed back to the grid some power at some point in time.
Okay, thanks a lot. So the next one was also referring to the bridgeless PFC. So for this below 1 kilowatt converter, why not use conventional boost converter?
Well, the answer is really in the slides is to get higher efficiency. So yes, it depends, of course, of the application and the requirements, because this will tend to cost more. There are more active switches and a more complex controller. So it means it will cost more, but it will have a higher efficiency. So there are cases where it might be more interesting to use the totem pole PFC because the density can be higher, the efficiency can be higher at a higher cost. A more classical boost PFC running CCM or CRM, depending on the power, will cost less, but it will have a lower efficiency. So it really depends to what you're trying to achieve.
Okay. Next one is to have less current harmonics, CCM is better than CRM, right?
Yes, that's normally true. That's normally true. Yes. So again, it's always you have to select the control method, the topology, depending on what you're trying to achieve. What is more important to you? Is it the size? Is it the cost? Is it the efficiency? And there's never or rarely only one answer to the question or only one solution that can be used. So you have to make your choice depending on what you're trying to achieve and what's more important to you. If you're driven by cost, then you will always try to use the cheapest and simplest solution that gives enough results or enough performance. So in that case, yeah, a CRM solution, even though it might have higher harmonics and higher EMI, might still be cheaper, even if you have to have some maybe a bigger filter in front or something like this, or that you have a little less PF or a little higher distortion. But if it's good enough and you achieve your target and at a good price and the size is acceptable, then you will use the cheapest one. So it really depends on what's driving you and what's the most important.
Thanks a lot, Nicola. Next one is, how do we actually measure active power and apparent power practically?
So practically, there are power meters that you put in front, and it will give you exactly the active power, reactive power, and so that's very easy to measure.
Okay, next one is, how do you manage the dead time in discontinuous mode with GaN semiconductors? SR3 quadrant diode is quite critical.
Okay, let's see. Maybe this will be a bit long to get into that. Yeah, I'm not necessarily I've not necessarily prepared this. So why don't we answer later on this? I think the dead time in discontinuous mode is only for light load conditions. So the current is low in this condition. So I think that might be one part of the answer. But yeah, I'll come back to that maybe in a we'll reply to this
Via
this
email.
person
Okay,
offline.
good, perfect. Next one is, do your controllers support bidirectional PFC? Or any comment on that?
So at the moment, no, we don't have a controller that supports bidirectional, but it's something that we're working on because it's yeah, we see that there's definitely an application for it, and it will become interesting at some point. So it's something that we might have in the future, but we don't have it at the moment.
Okay. Next one is for totem pole, as long as we run at 100 kilohertz, it shouldn't matter if you use GaN or silicon, right?
No, I don't think this is true. No, I think even at 100 kilohertz, you will benefit from using GaN. You will have less switching losses potentially, and yeah, no, I don't think this is right. I think you can get some improvement by using GaN even at 100 kilohertz. Yeah.
Okay. So there's one wish for next time, and the person is asking if you can add some more content for three-phase PFCs in the next.
Yes, sure. We can add a lot more content. Yeah, three phase or other improvements that can be done. We can discuss also stability, etc. Yeah, the format of this webinar is such that we have to choose our topics. But yeah, why not talk about this in the next one? Thank you for the suggestion.
Thanks for the feedback. Next one is because for 440 volt input, GaN would not be sufficient, right?
Yeah, well, this is a good point. Yeah. In that case, maybe silicon carbide will be also to be considered instead of GaN and instead of silicon MOSFET. And again, I'll give that same answer that yeah, depending on your exact needs and your target, also efficiency, cost, and so on, then maybe the silicon MOSFET is good enough, or maybe you need something that has a little less losses at the given point of operation. And then if GaN is not sufficient because of input voltage too high, for example, then maybe silicon carbide is the solution. So it really, again, depends on what you're trying to achieve.
Okay, thanks. Next one is the MP45000 controller available on the market?
So this is a new part that we are just starting to sample. So it's available for sampling, but it's not quite released yet. It will come in a few months.
Okay, and the next one is the controller for bridgeless analog or digital?
Okay. It's let's see. If you're talking about this MP45000, it has some sort of digital core, but also part of it is analog. It has drivers and etc. But we have also other totem pole PFC, CCM totem pole PFC for higher power, which is fully digital. So yeah, we have both solutions. Yeah.
Thanks a lot. Next one is the gate drive more complex in totem pole compared to classic in regards to isolation potentials?
Well, if you compare it to a simple boost PFC with a freewheeling diode, where you only have one active switch, which is on the low side, then yes, the gate drive of totem pole is more complex because in the totem pole, we have two high side switches that have to be driven, with well, not necessarily isolated driver, but at least a high side driver. So of course, this makes it more complex and costly. Now, if you compare it to a synchronous boost, then there will also be a high side MOSFET. So in that case, there will be also one high side drive. But yeah, in practically, usually the controller for totem pole will be a little bit more complex because it needs to drive 4 MOSFET. But again, it will bring you some advantages that you cannot reach and some results that you cannot reach with the other one.
Okay, thanks a lot. Next one is totem pole recommended at low power levels?
Should I give the same answer again? Yeah, this again is it's not a question of being recommended or not recommended. It's really what you're trying to achieve. If you want high efficiency, very high power density with minimum hotspot on your board and so on, then yeah, probably the totem pole PFC will be recommended. If you have plenty of room, not so many constraints, and you're targeting low cost application, then probably not. It's not recommended. So it really depends of what you're trying to achieve and what's your budget.
Okay. The next one is, have you observed additional EMI problems when using bridgeless PFC instead of normal PFC?
That is a very good question. There is one drawback of the totem pole PFC, and this might be also a subject for our next webinar, is that there are some higher common mode currents circulating, especially at the zero crossing. So when going from positive to negative alternance, which tends to increase the EMI. So in reality, for a given point of operation, it's most likely that the input filter will be bigger on the totem pole PFC instead of boost PFC. Although there are some enhancement techniques that can be used to minimize that. But yeah, the quick answer for this is yes, there tends to be higher EMI content due to common mode case, yeah, in the totem pole PFC.
Thanks a lot. The next one is, what is the roadmap or tendency for PFC IC controller, boost type or bridgeless type?
Well, the quick answer is there's room for both. As I was saying, it really depends on what you're trying to achieve. So there will always be a need for simple and cheap controllers, boost type, critical mode conduction, and there will be room for a more complex totem pole IC. So yeah, the roadmap is that we add totem pole control because it can bring some advantages, and there are some applications where it's the best choice. But also the roadmap for boost type PFC will stay there because there's still a market for it, and in most cases it is sufficient.
Good. I would also recommend to contact your local MPS sales guy or technical person, or you can also contact MPS now via our website, and we can see what kind of information can be shared. Good. Next one would be, can we use totem pole PFC for LED applications?
There's no reason why you couldn't. So yes, it can be used. Yep, for sure.
Okay. Then the next one is, the classical boost PFC has a bypass diode. Is it needed for totem pole PFC?
So that bypass diode is usually used to preload the output capacitor of the PFC so that there's not too much current going through the inductor and the diode. So it might also be needed in totem pole, or it might be possible to get away with it if we have the good thing about the PFC is that you always have a switch in series. So if you control that switch, you can actually make a slow inrush current limiter. So depending on the complexity of the controller, you might be able to not have that bypass diode. It really depends how the implementation of the controller.
Okay. Next one is, how to EMI mitigation techniques significantly improved PFC system performance.
I'm not sure what this is referring to. I haven't really presented any mitigation techniques in this webinar. So I'm not sure what this is referring to, Julian. So I will pass on this question. We can answer offline.
Yeah, perhaps you can, to the guy who asked this question, perhaps you can send an email to or fill out the form on our website at MPS Now and ask again, and we will come back about this question, or probably we might just answer the question via email if we find your email address. Next one is EMI perspective, which is better, CCM or CRM?
This is not so obvious to answer because it will also depend on the power level. Because in the CRM case, the higher the power level, the higher the peak current and higher the DI over DT. So at some point, it will probably be more interesting to be CCM than CRM, even though at lower power, the CRM should be better because it's running zero current switching, most likely zero voltage switching as well. So it should be better for lower power for CRM, but at some point, it will become more interesting to be CCM. Yeah.
Okay. And the next one is when AC line goes to zero, bulk capacitor pushed high current to AC line. Totem pole PFC topology. How solve this problem?
Yeah, so this will take too much time. Probably we're already past the hour. So there are ways to solve this, or there are techniques, let's say, that we can improve this. But yeah, the zero crossing in a totem pole PFC, as with a regular boost, by the way, it's a complex condition, and there are some even some patents to deal with this. So yeah, I will not go into details on this, but this is a good question. Yeah.
So we can take care about this in a next webinar, or we'll also come back via email. Let's Nicola, if you still have time, let's answer the questions which have come in now, and for all new questions which come in, we will also come back via email. So the next one is what would be the pros and cons of interleaving totem pole PFC? Lower noise, better thermal management.
Yes, I mean, this is in general interleaving, not only of totem pole PFC, but any PFC stage. Of course, the thermal management is better because you're spreading the heat into different IC, different spots, let's say, on the board. So it's always better. You also improve the input ripple, for example, by doing interleaving. So yeah, there are always advantages of interleaving. Of course, since you're doubling the amount of components, it has a cost and a size associated to it. Although the individual components tend to be smaller than if you do the equivalent power with a single PFC rather than interleaving, there's still some cost associated to it. But yes, there are definitely improvements on the heat dissipation because you have less hot spots, let's say. Or also the totem pole PFC by itself already is spreading the power into more ICs or more components. So it's also a little bit better for heat spreading, but yeah, interleaving is better.
Okay, thanks a lot. The next one is there a circuit that integrates all functions in one device to create a switch mode power supply, including the PFC control? This is to give a small and clean design.
Yes, there are. For example, we have this HR12XX family of parts at MPS, which is we call it a combo controller. So it has both the PFC control, the PF control, plus the DC to DC conversion stage into one controller. So this is PFC plus LLC or PFC plus flyback. And so yes, this exists. Of course, the MOSFETs are usually external for the reason of at this high power, we want to spread the heat and not have everything in one spot. So the MOSFETs are external, but the control, it's one common controller for both stage, the PFC and the DC-DC. So yeah, this exists. HR12XX family, we have many parts like this.
Okay, next one is, does MPS have any bridgeless specific IC controller?
Yes, at the moment we have one digital CCM totem pole PFC controller, MPF 32010, and we're just sampling a new one, MP 45000, which is a CRM totem pole PFC for lower power. So at the moment we have two parts here.
Thanks, Nicolas. The next one is, some classical CCM PFC uses a controller IC without V-in sense. Is it possible for totem pole PFC?
Because the totem pole PFC needs to control that polarity selection MOSFET, it's really hard to do it without V-in sense. Now the V-in sense can be rather simple, maybe not necessarily a very complex internally with a multiplier and everything, because if you're running a totem pole in CRM, consonant time CRM, then you can probably get away with a simple architecture, but you still need that V-in sense anyway, at least for the selection of the MOSFET, unless you decide to not use MOSFET but use diodes instead. But yeah, this in that case, it's not. It will not be very interesting.
Thanks a lot. The next one is, can you suggest the PFC ICs that includes compensation, triangular compensation, PFC control law?
Okay, I think if you check the latest combo PFC plus LLC IC that we have, should be the HR1230. I think this one includes that that compensation. There might be more. I'm not completely sure off the top of my head, but yeah, at least this one should have it.
Okay. The next one is, how stability of PFC is affected when its load is inverter or any other SMPS. Negative resistance is constant power load. How does MPS mitigate problem in control being affected by input filter and load in ICs?
Yeah, this is a more complex question. Again, I think we'll reply to this one offline, Julian.
Okay, perfect. So we will also come back via email. Next one is, what is the approximate price increase from CCM mode 1 kilowatt to totem pole 1 kilowatt in percent?
CCM mode 1 kilowatt to totem pole 1 kilowatt. I honestly don't have the figures, the numbers right now. I expect there will be some price increase just already by the number of active switches. Just that already will increase the price. So it will depend on, of course, on the selection of the type of switches, if it's GaN or silicon or SiC, and yes. But I couldn't give you even an approximate price for totem pole, maybe 30%, but this is just a guess. So yeah, I don't have an exact answer for that.
Thanks a lot, Nicolas. And yeah, sorry.
The last question is for you.
Then last one is for me, and many people have asked if the slides will be available. As I said before, yes, we will send out an email with the PDF of the presentation, and you will also get a link to the recording of this webinar. So at the moment, I'm not seeing any new questions. So as we mentioned before, we will come back about the open questions via email. And yeah, thanks a lot for the feedback. We will take it into account for future webinars. I would also recommend to check our website regularly for new MPS webinars. And yeah, thanks again for joining today. And yeah, we are happy to welcome you in future webinars. Thank you, Nicola.
Thank you.
Bye, and yeah, have a great day or evening. Bye.
Bye-bye.